What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
Hi, and welcome to Fun with HO Scale Stuff. This is episode 17, and it's part 2 of the repurpose of my damaged laptop to run JMRI via a Bluetooth COM port. In episode 16, I introduced this latest project. And in this episode, my objective is to pair that laptop with the HC05 Bluetooth module. This is the Bluetooth module that I'm using for this project. It's sold on Amazon as a HiLetGo, that's HiLetGo, HC05 wireless 6-pin module. I'll leave a link in the description on where you can actually buy this if you choose to. The module was manufactured in China by a company called Guangzhou HC Information Technology Company Ltd. It's a kind of a mouthful for that particular company, but I don't know that HiLetGo may still offer several Bluetooth assemblies. The even-numbered modules, the -04 and the -06, are either a connection master or a discoverable slave device, while the odd number modules, the -03 and the -05, are configurable as either mode of operation. I chose the -05 just because it was what I saw on Amazon, but it is kind of nice to have a module that can be both the master and slave mode. I think the majority of cases people are buying the HC-04S or slave mode only version because they're creating an application that will always be slave to a controlling device like a cell phone or a laptop. For the instruction manual of this particular module, it's available online, and I also placed a link for that in the description section. The HC05 module actually consists of two main components. There's here the yellow arrow is pointing at the baseboard, which is equipped with a 6-pin header, as you can see. That header pins, the meaning of the pins actually, are actually stenciled on the back of the unit. I'm showing that here. I'll discuss these functions a bit later in the video. Mounted to the baseboard is the second main component indicated by the green arrow. This is a radio board that was designed by Cambridge Silicon Radio. CSR was a fabless semiconductor company located in Cambridge in the United Kingdom. This large chip on the radio board is a System on a Chip, or SoC. It has the CSR logo at the top, and it is designated as the BC417. It was part of a series of chips designed by CSR in their Blue Core 4 series, hence the BC4. After CSR was purchased by Qualcomm in 2015, Qualcomm created a new series of radio chips, the SoC that they call the BC5. I've read that the BC4 chips have been discontinued by Qualcomm since the release of their BC5. The BC4 system architecture is shown here. The system on a chip has 5 main segments. The baseband digital signal processor, or DSP, is that which modulates and demodulates the radio frequency specified as 2.4 gigahertz. The radio block provides the 2.4 gigahertz transceiver. The MCU, or main control unit, is a RISC processor. The firmware executed by the MCU is external to the SoC and is accessed via the I/O block's external memory interface. The code it executes is the CSR Bluetooth software stack. The term stack used here refers to a collection of independent components that function collectively to support the application. The document for the CSR System on a Chip can be found using the link I included in the description section of this video. The other big chip on the radio board is the NOR flash memory. In this case, it is a Macronix International MX 29LV VFBGA, or very fine pitch ball grid array package. This flash memory stores up to 8 megabits as 1 mega of 8-bit bytes, and it contains the CSR Bluetooth software stack. The desired intent for this project is to connect the two electronic devices, the Arduino and the HC-05. So it isn't quite enough information yet to make these connections. I need to know more about the specification of the electronic interfaces for the two devices. I have a fair understanding of the Arduino interface. It's a 5-volt output, but the inputs are also expected to be about 5 volts, but I believe there's a range. So I want to take a look at the actual electrical specifications for the two interfaces and make sure that we connect them safely. I don't want to damage this. That's what I'm going to do next, is I'm going to examine the electrical requirements for these two devices. I'm starting with the Bluetooth modules. The electrical specs shown here are for the CSR radio board. I'm using that because the baseboard it's mounted to adds no value. It's just a routing of select radio board signals to the header pins. I see in the USB and UART section that for the signal board's universal asynchronous receiver transmitter, or UART, that the UART_TX transmit signal has a CMOS source with a pull-up resistance. Also, this signal is tri-statable. Well, tri-state just means that the signal's CMOS driver is detached when not actively transmitting. And that pull-up resistance assures that the output will be at a high level voltage while the CMOS driver is detached. I also see that the UART_RX signal is pretty much the same as the transmit, with the exception that it's got a pull-down resistance, and that is going to cause the receiver, the UART receiving electronics will see a low level voltage whenever there's no signal on that line. I see in the recommended operating conditions section that the supply voltage to the VDD_PIO has a voltage range between 1.7 volts and 3.6 volts. What this means is that the signal applied to the radio board's UART_RX signal that must be no greater than 3.6 volts. And coincidentally, the High-Let-Go board's signal stencil on the back of the baseboard indicates the RXD and the TXD signals are level 3.3 volts, which agrees well. In the same section of this specification, the supply voltage, it's called VREG_IN, has a range between 2.2 volts and 4.2 volts. And there's a footnote at the bottom that amends the maximum voltage from 4.2 volts to as much as 5.6. But the radio frequency is not guaranteed above 4.2 volts. That might explain why some hobbyists have Bluetooth performance issues with this module when they're using the 5-volt supply of the Arduino. It may be a risk worth noting just in case. Note that CMOS inputs require very little current, since CMOS logic is predominantly a voltage sense logic. The electrical specifications shown here are for the Atmel Atmega 328, which is the microcontroller used on the Arduino Uno. The section called Serial Bus Requirements documents the input low and high voltage ranges. The low logic level is between ground and 0.3 volts. The high logic level is anywhere between 0.7 and 5 volts. The 5 volts is the 5-volt supply voltage from the Arduino's voltage regulator. The absolute maximum is 6 volts, but again, the Arduino board's voltage regulator creates 5 volts for the microcontroller. The graph at the bottom is showing the digital output voltages for the 5 volt supply. Because the radio board on the Bluetooth module has CMOS inputs, the current demand for any microcontroller output is essentially none. The graph's top left corner shows that for any temperature, the microcontroller's output will be 5 volts at 0 current demand. I think that I have covered all of the electrical requirements to make the connections between the Bluetooth module and the Arduino. What I need to examine now is the functionality of the 6 pins available on the Bluetooth module's header. The HC05, RXD, and TXD signals are clearly for the serial communications with the Arduino. It's important to note here, though, that the Arduino's USB port and its RX-TX interface pins share the same serial I/O pins on the board's microcontroller, the Atmega328. Because of this, if the Arduino's TX and RX pins are used to interface to the HC05 module, then the module's serial connection must be disconnected whenever the USB port is being used. Initially, this will be my approach, but later I plan to use the Arduino software serial library and connect using a pair of digital I/O pins that will allow me to use the USB port for sending and receiving data to and from the Bluetooth channel. Also pretty clear are the GND and VCC pins. I did note earlier that the VCC at 5 volts from this Arduino may cause an issue with the radio board's performance. It prefers a maximum voltage of 4.2 volts, not 5 volts. So we'll find out. The state output is what I believe is from the radio board's PIO port as one of the WLAN_active or BT_active signals, and I'd say most likely it's the second one. It's really not that important, but I'll experiment a little bit with that. The EN input signal is evidently an input that is monitored by the CSR software stack code. The BC417 System on a Chip documentation identifies the 2 operating modes as master or slave. The clock in the radio signal is digitized using pulse code modulation when in the master mode. When it's interfaced as a PCM interface slave, it uses that clock from the master. The CSR software uses the state of the EN signal to switch between these 2 modes. So I've decided to make a connection diagram. The Arduino can be depicted and the HC05 can be depicted as follows. It has a header mounted on it with 6 pins. And I've decided that I'm not going to use the enable, so this one is not going to be connected. So initially, oh geez, there it is, looks like an RX. I want to connect is the power and ground. So starting with the power, I'll make these connections directly. If I have a Bluetooth problem from the 5 volt supply input, then I'll reduce the HC05's VCC voltage to the recommended value. My plan is to add an LED to the Arduino board, which will be illuminated as long as the state output from the HC05 is active. So I'm going to connect it to a digital input. And that would be digital input 2. The transmit high output from the HC05 is only about 3.6 volts. However, the Arduino digital input will see any voltage between 0.7 and 5 volts as a high. So this will work fine. And that will be connected directly to the receive. So that leaves this transmit and receive here, which again, the receive on the HC05 is supposed to be 3.6 volts. So this means that I've got to reduce. This is a 5 volt output and it needs to get reduced. So what I plan to do, we'll call this R1 and call this R2, and we'll connect R2 back to ground, and we'll take the R1 signal output and we'll send that back to there, so that this then must be 3.6 volts here. And since this is a CMOS input, it requires 0 volts, or pardon me, it requires 0 amps. Essentially just the voltage. So I don't have to worry too much about what R1 is equal to, because it doesn't need to pass any voltage to speak of. So it could be a very high resistance value. Whatever I choose for R1, I have to choose R2 such that the proportional division of the voltage 5 volts between these two resistors gives me 3.6 volts on this second resistor, so that the input to the RX will be 3.6 volts. This combination of resistors is referred to as a voltage divider. What remains is to select the two resistors, the R1 and R2. I have, let's see here, this tub of resistor values. I've salvaged some of them and purchased some of those, and that's my basic resistor collections. But before I select any from the tub, I want to note that, as stated earlier, the RXD input to the HC05 draws essentially no current. So the 5 volt TX signal from the Arduino will be entirely imposed across the two resistors that I choose, the R1 and R2, because there's no current going into here. There's no load outside of these two. Okay, I want to keep the current through the two resistors, R1 and R2, small. So I'm going to start with a very ambitious combined resistance of about 1 megohm, which would, between the two resistors, would produce roughly, let's say it's 5 volts over 1 megohm, and that would equal 5 microamps. So there's that. 5 microamps, which is plenty small current being drawn through from the TX signal of the Arduino. Since the R2 resistor, it must be producing no more than 3.6 volts. When the Arduino's TX signal is 5 volts, the desired voltage across this resistor R1 is going to be 5 volts minus 3.6 volts, which equals 1.4 volts. So we're going to have 1.4 volts here. Okay, so just looking at the 1.4 volts with respect to the 3.6 volts, it's roughly 1/3 of it. So the R1 resistor should be selected to be roughly, would be about if I was really hoping to get 1 megohm, it would be 1 megohm over 3, which is just equal to approximately 300 K ohms. All right. So I'd be shooting for about 300 K ohms for this value. And R2 then would be roughly, because of that, R2 would be roughly 700 K ohms in that vicinity. Just because it's 2/3 of the 1 meg. Well, I wanted to find the value of R2 first because it's, as I proposed, 700 K ohms, and that's a fairly large value. So I did search through my little bucket of resistor values, and I couldn't find anything that big. But I did find was a value of 430 K ohms. So I decided to use that one, and I still have reasonably small amount of current flowing from the 5 volts back to ground through the 2 resistors. So, so starting with a 430 K ohm resistor, I can figure out then what the R1 value is. But just as an aside, I thought I might mention that the way I searched for the larger resistor value was that the resistors, as some of you may not know and some of you probably do, but anyway, I'll show you. Let's say that's a resistor, and they have color bands. There's like a color, and then there's another color, and then there's another color, and then there's yet another color. And the colors on the resistor band are black, brown, red, orange, yellow, green, blue, violet, and what comes after violet? Gray, white, and then there's gold and silver. So how that works then, for those who may not know, is that the first 2 colors on the band are the first 2 digits of the resistor's value. And then the third color band is how many zeros to place after the first 2. And then this final one here is a precision value. We'll show you what that is. But you have black, brown, red, orange, yellow, green, blue, and then it was violet and gray. Then there's white. And then for the precision, there's 2 colors. There's gold, and then there's silver. I'll call SVR like that. Where gold is going to be 10%, and then silver is actually 1%. And those are precision resistors. So this color scheme right here, it starts out with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So those are all the digits necessary to describe these different colors. And as I mentioned, on the third color is the number of zeros. And I mentioned that I used a 4. So I have some number XX and then 4 zeros. That means then that it's going to be some 100 K ohms, depending on the lead color. And so as I sifted through all those resistors, the only thing I could find, it was yellow. So it was a 4. And it was 400 K ohms of some value. And then it was orange, so it was 3. And then it was yellow, as what I was looking for was for these 4 zeros. So it was 430 K ohm. Now, having chosen a 430 K ohm resistor for R2, then I have a simple method to find out what R1 should be. And as we recall, there's got to be 1.4 volts, and that's what's going to be over R1. So if this, it's kind of straightforward. If this resistor R2 has 3.6 volts, I know what the current is through that resistor in order to produce 3.6 volts. I use the voltage is equal to the current times the resistance. That's a simple rule. And then so just using that simple rule, then I can say there's some current here for a 430 k ohm resistor that has 3.6 volts is just, what is that current? And so you can say that the current is equal to the voltage divided by the resistance, which is equal to the 3.6 volts divided by the 430 k ohms, right? And that just equals about, well, approximately, let's say it's approximately equal to 8.4 microamps. So if I have 8.4 microamps here, and I don't have any current going into the HC05, then I have to have 8.4 microamps going through this resistor as well, R1. So easily said, R1 then, we'll say this R1 has got to be roughly, we're going to try and get it close to it, but it'll be 1.4 volts divided by the 8.4 microamps. And that value turns out to be a 167 k ohm resistors. What I found is I went back in scrounging and I found a resistor, and it was pretty doggone close. The value I found was brown, orange, yellow, which is 1, 6, and then 4. Okay, so if we take that, it should be 160. The 4 zeros are 160 k ohms, which is pretty close to that, what I wanted. So that one will do. So then R1 will be 160 k ohms. So what I'm doing right here, as you can see, the voltmeter is on volts DC, and I'm reading a voltage, and that is the voltage that's across R2. R2 is the 430 k ohm resistor right there. And it's just a little bit of detail here. This lead here goes back to ground. This lead is on ground, and then that would be R2. So by connecting here, I'm looking at the voltage across that resistor, which is our 430 k ohm resistor. And then of course that's R1, or 160 k ohm. And that 3.5 is just right. It's less than the 3.6, real close to it though, and it's just going to be perfect. Okay, so now that I've verified that my voltage divider is producing a safe voltage for the HC05's RXD signal input, I've taken all of that apart and I've put together the connections to be able to power up the HC05 module for the very first time and actually apply a serial signal from the Arduino to it. I don't really plan on sending it any signal yet. I just want to see first off is whether this unit powers up correctly. The unit has an LED on it, and we'll look at that in a second, but that LED will tell me that it is not joined with anything. So having that blinking signal will tell me that this thing is functioning, and it's probably functioning correctly. So the connections you see on here is the red is the power, green is ground. I had to jumper it over here because that's where the voltage divider circuit is. The blue is the transmit data. The orange, it's kind of stuck back in there a little bit, but the orange is the receive data. And the yellow, in the end, is the state signal coming back to a digital input. So now I'll power up the Arduino board, which in turn will power up the HC05 board. So here's power. And I think you can see that blinking there. So the blinking, I know red blinking is always like a cautious thing, but actually what that means for the HC05, according to its documentation, is that 2 blinks per second just indicates that it is not paired with anything. So it's working, and this is what I wanted to find out. Everything seems to be just fine. So the next step now is to see if I can pair it with a Bluetooth device. To this point, the Arduino Uno contained no code. I created and labeled the sketch here that you're looking at to assist my effort to pair the HC05 with my defective PC. In data mode, which is the default when the EN signal is not connected and is low, the device is a serial connection. In AT command mode, which is sometimes called the master mode, the Arduino's serial port connection to the HC05 changes from 9600 baud to 38,400 baud. This mode allows the AT commands to be sent to the HC05 that have a variety of configuration options, such as changing the module's name. Also, this mode enables the HC05 to connect to a Bluetooth device that is in the data mode. As many people already know, the Arduino sketch is comprised of two sections. The setup method here starts by configuring the Atmega 328's UART for 9600 baud with the defaults of 8-bit data, no parity bit, and 1 stop bit. This configuration matches the HC05's radio board's default serial configuration. I've also configured the digital pin number 13 as an output. Arduino digital pins all default to inputs. The right sets the pin 13 to a logic low, and then this pin is used to turn on and off a green LED that was added to the Arduino board. The setup method is executed only once when the power is applied. The loop method is executed continuously after the setup method completes. This simple method checks for input bytes in the serial input buffer, and if any are found, the data bytes are read from the buffer and just discarded. When an initial byte is detected from a Bluetooth channel, the LED will be turned on. My next Arduino Bluetooth sketch will be a little bit more interesting. I've transferred the sketch into the Arduino, and I'm going to demonstrate now the process of making the pairing and the connection with my damaged Windows 11 laptop. You might recognize this guy from a previous episode. Note that the pairing step only means that the two Bluetooth devices recognize each other. A connection is slightly different, and it takes place when a serial channel is established. I'll power up the laptop and I'll show the process of pairing now. With this PC on now, I'll next power up the Arduino, which also powers on the HC05 module. The rapid blinking of the LED of the Bluetooth module here means that it's ready to pair. To pair it, for my experience, required a couple of steps. First, I have to tap on the Bluetooth icon. I have to tap each time because, as I said, the serial ports don't work, so I don't have a mouse. Okay. So that displays this Bluetooth information. The next I select is Open Settings from this pick list. So we'll go down here to the bottom and tap Open Settings. So that displays the Bluetooth devices. When I initially did this pairing attempt to add the device, which is that button right there, I had a heck of a problem with it. It did not recognize the HC05 device. And what I discovered was that I had to change the Bluetooth device's discovery, which is right here, to advanced. It's already there right now, but the two choices you have are either default or advanced. And I found that with the advanced setting, the PC's Bluetooth drivers could see the HC05. With that set to advanced, I then click on Add Device. So tap that. And then the next thing I do is click on the Bluetooth category in the Add Device pop-up. Now you see that the HC-05 device is now showing. So I can pair that. I simply select this device here, and of course it's pairing. And the next thing it wants is the device's PIN code. And it turns out that this PIN code is, we'll go to this field, is 1234. And I just click connect. So now it says it's connected. But notice now it changed to HC-05 not connected. So it's paired, but it's not connected. And now notice also that the HC-05's red LED is still rapid blinking. And what that means is that it's still not connected. But once it is connected, that blinking will subside to a very slow blink. Now, whenever the HC-05 is paired with the Windows 10 or 11, the operating system will allocate a COM port. This is in addition to any COM ports that already exist. So by selecting, done, and close this, and by selecting Device Manager, you can come down to ports, and you can open ports, and you can see here that I have obviously no COM ports on this PC because the serial hardware has been damaged. But now I have two standard serial ports. It always seems to add two for some reason. But anyway, there are the serial ports for the Bluetooth serial connection to the HC-05. So I rearranged the computer so the screen's a little bit more visible here. And you can see again that even though the devices are paired, that they're not yet connected. You can see the flat rapid blinking on the HC-05. So in order to get a connection, establish a channel, I downloaded and installed this application called Bluetooth Serial Terminal. What it's going to do, it already recognizes that HC-05 is available, and so I click connect. It says it's connecting, and I want you to now notice that the blink rate period is much different. That indicates, it's indicating that it actually has a connection now. So if I were to go into transmit, enter some characters and send them, you notice that the green LED came on. And as I had shown earlier in the Arduino code, that whenever it sees any characters coming in, it turns the LED on. So that verifies that there is in fact a connection between the PC and the Bluetooth channel to the Arduino. Okay, well, with the Bluetooth pair and connection completed successfully, I'm satisfied with this part of my effort to establish a means to have a defective laptop running JMRI via a Bluetooth channel to control my locomotives and accessories. Providing this still leaves a number of things in this effort needing investigation. In my next video of this series, I will attempt the connection of the JMRI application running on a defective PC and display the serial data on my new PC. Stay tuned as things are about to get a bit more interesting, which, by the way, if any of this was interesting to you, please consider adding your like for this video. And if you didn't like it, I would really appreciate your comment suggesting how I might improve my videos. Thank you so much for watching.